Hi everyone, I am Prithwish. I am a PhD student in computer science at Georgia Tech, and today I'll be presenting our joint work with Sam Davidson, Bhavna Bhaskar, Andre Khan, Anup Deoras, and Lauren Callow from the Amazon Web Services. I'm excited to talk to you about TerraFormer, a system for automating infrastructure as code using large language models, fine-tuned via policy-guided verifier feedback. And broadly, this work sits at the intersection of two rapidly evolving fields, cloud infrastructure automation and AI-assisted software engineering. So let's begin with a brief introduction. So just to introduce the problem space, in modern cloud-based software development, infrastructure refers to the underlying components needed to run applications. And this includes compute resources, OS, networking, etc. And most often, developers need to manually set up or update these components. And that usually means running command line tools or clicking through cloud provider consoles. But that's a tedious process. And importantly, it lacks reusability and version control. So it can lead to inconsistent environments. So this is where infrastructure as code or IaC comes in. It lets us define and manage infrastructure through high-level machine-readable configuration files, enabling us to deploy the same infrastructure repeatedly and consistently. And popular IaC tools include Terraform, Kubernetes, and CloudFormation. And among these, Terraform is one of the most widely used. However, even for skilled engineers, setting up moderately complex infrastructure can take hours, and human-written configurations frequently introduce security vulnerabilities. So automating IaC generation can save significant time and reduce security risks. So just to give a quick background, this is what a Terraform configuration looks like. It's written in HCL, which stands for HashiCorp Configuration Language. It's a domain-specific language and supports multiple providers and resources which can have interdependencies between them. Now take this example on the left. It declares two providers and two resources, and as shown by the green arrow, these resources have an interdependency between them. So with that context in mind, our work tackles two core objectives, IaC generation and IaC mutation. So the first objective is IaC generation, and given a natural language prompt describing an infrastructure, the goal is to generate the corresponding Terraform configuration. So formally, we want to learn a function f that maps natural language prompt to Terraform such that the output is A, syntactically correct, B, deployable, and C, aligned with the user's intent. And the second objective is IaC mutation. So here, given an existing Terraform configuration and a natural language prompt describing the change, the goal is to generate a mutated configuration. And this mirrors real-world workflows more closely because developers often tweak existing scripts rather than starting from scratch. And here again, the output has to be syntactically correct, deployable, and should reflect the user's requested change. So what are the challenges for LLM-based IaC automation? So we identified four. First, data scarcity, that large high-quality IaC datasets do not exist due to privacy constraints. Second is capturing coder intent. So LLMs struggle with IaC's strict syntax and hallucinate complex resource dependencies. Third, mutation is underexplored. So editing existing infrastructure is fundamentally different from generating from scratch. And fourth, evaluation is a bottleneck. Cloud development is too slow for inference time verification, and proxies like BlueScore, they cannot guarantee deployability. So overall, this motivates a neuro-symbolic approach that tightly integrating LLMs with symbolic reasoning, formal verification, and self-correction. So here's what I'll cover in the rest of the talk. We have covered the introduction and the problem setting. Now I'll walk you through the proposed method, and finally I'll end with the experimental evaluation and concluding remarks. So let's start with the first part, our automated dataset curation pipeline using LLMs and formal verification. So we constructed two large-scale datasets for Terraform automation, TF-Gen for IaC generation and TF-Mutation for IaC mutation. So TF-Gen contains 152,000 infrastructure scenarios, and each instance consists of a natural language prompt, a target configuration, and a formal policy that captures the constraints. It is 330 times larger than IaC-Eval, and every example is validated using formal verification tools. And on the other hand, TF-Mutation contains 52,000 mutation scenarios, and this is the first large-scale benchmark for IaC mutation. And as you can see from the table, Compared to prior benchmarks, both datasets feature significantly more complex infrastructure setup, which has more providers, more resources, and longer configurations on average. And in the next few slides, I'll walk you through how these datasets were curated automatically. So our dataset curation pipeline uses LLMs and formal verification in a loop. And all we need here are a corpus of human written code, which can be erroneous, a general purpose LLM, and a compiler or verifier that checks syntax and semantics. So here's how it works. We identified three increasingly strict stages, namely correctness, deployability, and policy compliance, and we repair codes progressively as per these stages. And if you follow the diagram on the bottom right, that's the fundamental loop we use, and each configuration is run through a verifier. So if the errors are found, the error certificate is extracted and the LLM sees both the code and the error message and suggests a repair. So we repeat this loop until the code passes verification. And what's powerful is that this approach is completely language and domain agnostic, so we can apply it to any IaC tool or other programming language just by swapping in language specific components. So the first step is data collection. We source from TerraDS 62,000 GitHub repos of real-world Terraform configurations. And because HCL is declarative, we concatenate all .tf files using within each module into one unified configuration, giving us around 279,000 configurations. However, when analyzed with Chekhov, we found widespread misconfigurations and security issues, meaning many of these are not deployable as is. So this motivates the next step. So in steps 2 and 3, we verify and repair syntax and deployability. So syntax is checked using Terraform validate and deployability using Terraform plan. And for any configuration that fails, we run our multi-turn iterative repair loop where an LLM receives the error certificate from the verifier and attempts a fix. And this process repeats until the configuration passes. And finally, in step 4 and 5, we generate the remaining two components of each instance. So for the natural language prompt, Foundation LLM synthesizes a natural language description. And for the formal policy, a Foundation LLM generates a policy in the language called Rigo, and it encodes the prompt's intent, again with a multi-turn repair loop. Now let's move to the second part of the methodology. So fine-tuning Terraformer via policy-guided verifier feedback. So we warm start training with supervised fine-tuning, and the LLM takes a natural language prompt and generates a Terraform configuration, which is compared against the reference configuration using class entropy loss. And what makes our SFT effective comes down to three properties of our dataset. First, high quality supervision. So every reference configuration is verified and deployable. Second, diversity. Each prompt is paired with multiple cloned configurations, capturing different valid implementations of the same request. And third, formal equivalence guarantees. So cloned configurations are proven equivalent under formal policy, and this ensures that semantic consistency is existing despite surface variations in our dataset. So next, we apply reinforcement learning with verifier feedback. So instead of comparing the generated configuration against a fixed gold standard, we evaluate it using formal verification tools and use that feedback as a reward signal during fine-tuning. So the reward function here is hierarchical, as shown in the red box. So if the code is not compilable, the reward is 0. If it's compilable but not deployable, the reward is 0.5. And if it's deployable, the reward is 1 plus the fraction of formal policy rules satisfied. And this gives fine-grained Oracle-based feedback that rewards syntax, execution, and functional correctness. And this enables the model to generalize to harder and out-of-distribution scenarios. Now let's move on to the experimental evaluation, covering our setup, baselines, and results. So we evaluate on two tasks, first IaC generation, second IaC mutation, and we measure 5 metrics across 2 dimensions. So for practical applicability, we compute compilability, deployability, and correctness. And for security and best practices, we compute linter compliance rate using TF-Lint and security compliance pass rate using Chekhov. And for TerraFormer, we built 2 variants by fine-tuning Coin 2.5 Coda 3 billion and the 14 billion. So we compare against 17 state-of-the-art LLMs in total, ranging from 3 billion all the way up to 671 billion parameters. And these baselines span 4 categories. First, large foundation models like Sonnet 3.7. Second, distilled variants where large models are compressed into smaller backbones. Third, instruction-tuned LLMs like Llama 70 billion instruct. And fourth, code specialized models such as DeepSeek Coder, Cohen 2.5 Coder, etc. So overall, we believe that this comprehensive and diverse set of baselines that we benchmark against. So here are the results for the IaC generation task. A few general trends. First, accuracy improves with model size. Second, among frontier models, Claude Sonnet 3.7 and DeepSeek R1, they consistently lead. Third, distilled variants of DeepSeek R1, they tend to hallucinate resource names and attributes. Fourth, code specialized models outperform general purpose ones of the same size. Now focusing on TerraFormer 14 billion, the supervised fine-tuning alone improves correctness by 8.7% on IaC-Eval, and adding reinforcement learning further boosts correctness by 15.9%. And across all metrics, on IaC-Eval, TerraFormer achieves the best deployability, linter compliance, and security compliance. And notably, TerraFormer outperforms model nearly 50 times its size. And moving to IC mutation task, we see similar trends. The same general patterns 1, 2, 3, and 4 hold, as I mentioned in the last slide. Focusing on TerraFormer, the gains here are even more pronounced. So for the 3 billion model, SFT improves correctness by 12% and deployability by 28%. And adding RL pushes those further to 18% and 35% respectively. And for the 14 billion model, SFT improves correctness by 8.3% and RL further boosts that to 19.6%. So overall, TerraFormer 14 billion achieves the best correctness, linter pass rate, and security compliance, and again outperforms models nearly 50 times its size. So I'm almost at the end of the talk. Let me close with some concluding remarks. So as we saw, IaC automation is hard. Today, even the best LLMs struggle with this. So to solve, we introduced TerraFormer, a neuro-symbolic framework that fine-tunes LLMs using hierarchical verifier feedback. And we also built two large-scale formally verified datasets, TF-Gen and TF-Mutation. And from our results, TerraFormer outperforms frontier models like Claude Sonnet 3.7, DeepSeek R1, and GPT 4.1, models up to 50 times its size. But the broader implication goes beyond the tool Terraform. So the core insight is that we can generate verified data using automated reasoning tools, then fine-tune with hierarchical verifier rewards, and it's a general recipe, and it applies to any formal language task like code generation, mathematical reasoning, and hardware design. And TerraFormer is a proof of concept that small, efficiently trained models can match or exceed massive foundation models when guided with formal feedback. And that wraps up my talk. Thank you.